Hello everybody, and welcome to the beginning of sections 5.1 and 5.2 in the workbook. We are looking at page 109, and then the topic is the second fundamental theorem of calculus. So the best way to introduce this topic is just to start with an example. Let's read this together, see what this is asking us. So let f be the function shown in the diagram to the right. Here's the picture that they're giving us, and define a new function as a of x equals the integral from 0 to x of f of t dt. So we have a function a that's defined in kind of an unusual way in terms of an integral. So to get a feel for how this function is behaving, let's start by seeing if we can graph this function. Okay, so we're going to go back to a technique that you might have learned in algebra. When we've got a function that's unfamiliar to us, one thing that we can do is start by just plotting some points. Okay, so we're going to make a table here of x versus a of x. And we'll try to pick some relatively nice numbers for x here. So how about if we start with 0, and then maybe 1, 2, 3, and we'll throw in 4 as well. Okay, and so for each of these numbers, we need to use the definition of our function, which is sitting up here, and notice that the numbers x that we're plugging in, they end up as our upper limit of integration when we do this. So for example, if we want to calculate a of 0, we're going to be replacing all of our x's with zeros, which means that this upper limit will become 0. So what we actually need to calculate then is this integral, the integral from 0 to 0 of f of t dt. Well, if you think back to what we talked about with integrals, integrals really represent areas. And so to get a number for this integral, we just need to ask ourselves how much area is under the curve f of t from 0 to 0. Well, since we start and stop at the same point, there's no area under the curve, and so we actually get 0 for this integral. Okay, now we're ready to move on to x equals 1. Same idea. Now we're replacing that x with 1, and the integral that we need to calculate looks like the integral from 0 to 1 of f of t dt. Okay, that again is about area, so we'll go over to the right here with our function and try to highlight the area between 0 and 1. Okay, that's what it would look like if we shaded it. And notice that that's a rectangular area. We can see that the height of the rectangle is 4 and the width is 1. So the area is just going to be 4 times 1, or 4. That's our output. Okay, and we keep going this way. So now, next up is x equals 2. So we're integrating from 0 to 2 of f of t dt. So now we're starting at 0 and going all the way to 2. So we're shading more area. And now we've got a rectangle that has a height of 4 and a width of 2. We just doubled our area and got 8. Okay, how about a of 3? Well, now we're talking about the area between 0 and 3, so we've just added this area. That's triangular. And notice that the area of that triangle is half of the area of the two rectangles that we added. Okay, so we're going to get the 8 that we had before, and then we're going to add 2 more. That's the area of that triangle that we just added. Okay, so we're going to get 10 for this. Okay, and then what about a of 4? Well, now we're integrating from 0 to 4. And so our function goes below the x-axis. So we're shading in this area, and you might remember when we talked about integrals, what is it that happens when the area is below the x-axis? Well, we end up subtracting it, and these two triangles, I'm just going to highlight those in red, have the same size, so we just subtracted that same area of 2 that we just added at the previous step. So we're going to take the 10 that we had at the previous step and then subtract 2, which is the area of that triangle that's below the x-axis. That's going to take us back down to 8. Okay, so we have a table of values here, and we can plot these points to see what a of x looks like. All right, so just to declutter, I'm going to get rid of some of the shading that we did here. And now we'll go ahead and plot the points that we have, starting with 0, 0, that would be here, and then 1, 4, that's here, 2, 8, and so on. Okay, 3, 10. Now let's be careful with our scale. Notice that we're going by 2, so 10 would actually be here. And then 4 and 8 takes us back down to here. Okay, and if we play connect the dots, notice that the first 3 points lie on a straight line. Okay, so that's the first part of our a function. Then it gets a little bit interesting. Okay, for these last 3 dots, we could ask the question, do those dots connect with straight lines, or is there maybe a curve involved here? Okay, so to investigate that a little bit further, maybe what we could do is take another point and plug it in and see what happens. So for example, what if we were to plug 2.5 into our function? Okay, well, what we'd be calculating then is the integral from 0 to 2.5 of f of t dt. Okay, we already know what the integral from 0 to 2 is. Okay, that was kind of those 2 rectangles together, which gave us 8. But then we're adding a little piece of area that looks like this. It sort of splits into a square, okay, or a rectangle and a triangle. And the question is, how much extra area is that? Okay, well, this square down here, if you look carefully at it, that adds 1 unit of area, and then this triangle adds an extra half. So we just added 1.5 units of area, and we get 9.5. Okay, and the question is, where would 9.5 be on our scale? Well, 9 is halfway between 8 and 10, and so 9.5 would be half again, about there. And if you look carefully, these 3 points are not on a straight line, which tells us that there's some curve to this. Okay, and if we were to go over here maybe to 3.5 and kind of do a similar experiment, we would discover that that's also curved. Okay, so roughly speaking then, this function that we've defined a of x looks like the red graph that we just drew. Okay, now let's take a minute though to pull all of this together. So is there a relationship between these 2 graphs? Okay, we've got an f that we started with, and we've got this a that we graphed. Is there a relationship between those 2 functions? Well, I'll give you a hint here. If you kind of look at the graph of f carefully, I'm going to highlight one point here. Notice that f crosses the x-axis at x equals 3, and if we go up to the graph of a, notice what's going on there. We have a horizontal tangent line at that same point. Okay, another thing that we might notice is that if we look at the part of the graph of f that's positive, I'm going to highlight it in green here, notice that for those x values, the red graph is actually increasing. It's going up left to right. And then similarly, where the graph of little f is negative, the graph of a is going down. Okay, if you put all that together, it might lead you to believe that the graph of little f is behaving like the derivative of a. Okay, so let's list that as an observation here. So f appears to behave like the derivative of a. Okay, or said another way, we could say that the derivative of a of x appears to be f of x. Okay, and that's an observation that turns out to be correct, and we're going to pursue that further in future examples.